Hello, this is Building a Self-Healing System with SaltStack. My name is Gareth Greenaway. So just a little bit about me. My Twitter can be found on each slide in the lower right-hand corner. So if anyone is interested in tweeting about this talk, go ahead, by all means. I am a senior software engineer at SaltStack. I'm fortunate to spend my days writing open source software. If anyone has the opportunity, I highly recommend it. So this is Building a Self-Healing System with SaltStack. So before we begin, I wanted to introduce just some basic information, some Salt terminology and concepts, based on the concepts and ideas that we're going to look at. So SaltStack is originally written in Python. It began as a remote execution system, basically a way to run the same command across multiple systems. Similar in nature to tools like Fabric and Func, but it's not over SSH. So it's encrypted and done using the 0MQ messaging bus, so it's very fast. Because of the way that Salt was originally designed, adding things like configuration management was easy, and that was done through state modules. And because everything is done using the Salt API, adding additional components, some of which we'll look at later, was also relatively easy. As I said, everything is done over the Salt API, which is easily exposed for other purposes. So some of the Salt components that we're going to focus on today is the Salt event bus, which is the heart of SaltStack, and what allows it allows all the pieces to communicate. We're also going to look at Pillar. So Pillar is a static secure data store, specifically targeted at minions or minions, a minion or minions. We're also going to look at reactors. Reactors are small Salt modules that wait for specific events and react in some way. For example, running a specific module or state. We're also going to look at grains briefly. So grains are an interface to derive information about an underlying system. They're collected based on information like operating system, domain name, IP address, kernel, OS type, memory, and many other system properties. So devices within a Salt-controlled environment are referred to as Salt minions, and each device is controlled using a piece of software known as the Salt minion. The Salt minion daemon receives commands from the remote Salt master via the Salt event bus. So the device or server in the environment that controls the Salt minions is known as the Salt master. This device runs a piece of software aptly named Salt master. The Salt master daemon sends commands to the Salt minions via the Salt event bus. So a typical Salt setup includes a single Salt master controlling many minions. We can also have a setup with multiple masters controlling many minions. We can also have an option to run in a masterless setup. So we just have Salt minions, no Salt master. So within Salt, we use a concept called targeting. Salt targeting is the way one specifies which minion should run a command or execute a state by matching against host names, system information, defined groups, or any combination thereof. So we have a variety of options for targeting. The most common two are targeting using globbing or targeting using the minion ID. So globbing allows targeting of many minions using parts of the minion ID. In the first three examples, we're targeting all minions that the Salt master knows about with the command salt * test.version. So this will run test.version across all the Salt minions that the Salt master is aware of. Second, we're targeting any minion whose minion ID begins with the word minion. So in this case, we're running the same command, and any minion that matches has minion ID has minion in it at the start, we'll run that test version. And then third, we're targeting a specific minion and only that minion. Minion IDs are unique across your Salt infrastructure. So we can also target based on grains. As we briefly talked about, grains are system information such as OS version. So in this example, we're targeting any minion whose OS grain matches Fedora, and we're running the test.version. And finally, we can combine this targeting into using what's called compound targeting. So in this example, we're targeting any minion whose OS grain is Debian and whose minion ID begins with the text web serve. So the Salt event bus, as I said, is the heart of SaltStack and really distinguishes it from the other similar projects. The Salt Master and the Salt Minion each have their own events bus systems. The event bus is used by the Salt Master to publish commands to the Salt Minions, and then the Salt Minion uses the event bus to publish the return information for a job back to the Salt Master. And then the Salt Minion uses its own local event bus for locally run commands that need to interact with the running Salt Minion. So here we have a diagram showing the Salt event bus. In the middle, we have the event bus with the Salt Master and Salt Minions connecting into it. We have minions running on a variety of operating systems, including Windows, Linux, AIX, and some network devices such as routers and switches. On the master level, we can see the various components such as runners, reactors, engines, and the Salt API. We can see that the Salt Master is providing things like Pillar, the file server for providing state files, and handling minion authentication. So we also have a number of event types available. So we have authentication events, which are fired when a minion performs an authentication check with the master. We have start events, which are fired every time a minion connects to the Salt Master. And then key events, which are fired when accepting and rejecting minion keys on the Salt Master. These happen as a result of various actions undertaken by the salt key command. So we have job events. There's a variety of events here, such as when the job is sent out to the minions from the master, when a minion returns data from a job to the master, and each time a function inside a state run completes its execution. This option is disabled by default and must be enabled with the state events option. So we also have runner events. These are associated with Salt runners and include events for when a runner begins, returns, and whether a runner is part of the orchestration system. There are also presence events, which indicate the presence of minions connected to a Salt Master. And finally, there are a variety of cloud events. These events are fired when using the command salt cloud, unlike other events that are not fired on behalf of a minion, since the minion in question might not be running yet. These are events such as whether a cloud VM is in the process of being created, deployed, or destroyed. So there are a variety of ways that we can listen for events on the Salt event bus. Using the event function within the Salt state runner on the Salt Master, we can see all the events that are currently being sent to the event bus. And this is what a typical output from the command, the event runner would look like. So here we have a variety of events based on various commands. There's a test ping in there. There's a minion data refresh, and then there's an authentication event as well. So we can also see those events using the Salt API by using curl and providing an authentication token. And we can query the event bus using some Python code. So here we have a very simple Python script program where we're importing some Salt libraries, getting our configuration for the Salt Master, and then making a call to Salt utils event, get event to pull events and events off the event bus. So here's an example of what an event would look like as we saw when passing by on the event bus, if we ran a job on the Salt Master targeting all minions to run the test.ping command. So events are made up of two parts. The tag, which identifies the event that was fired, which we can see highlighted here in yellow, and the data that contains details about the event, also highlighted in yellow. Every Salt job has a unique job ID or JID, which is part of the tag and also included in the data for the event dictionary using the key JID. We also have the IDs for the minion that match the targeting type. In this particular case, only one minion called minion2 matched the targeting criteria. Once a job is completed, another event is generated that includes the return data. The tag for this job is very similar to the original event that was generated when the job was created. But we can see this job is a return job with the RAT included in the tag. The JID in the tag and inside the return data is also the same JID from the previous new event. And now the ID of the minion where the test.ping was run is included in the tag as well as the event data. If an additional minion has also matched the original criteria and has run test.ping, we would see an additional event that was returned with the same JID, but with a different minion ID in both the tag and the event data. As mentioned before, we can also have authentication events. Here's an example of an event when a minion first connects to a salt master, but has yet to have its key signed by the master. We can see that this is indicated with the key ACT and its value of penned. When dealing with salt events, it can be useful to be able to send events to the salt event bus. And we have a couple different options for doing that. We can send an event to the minion's local event bus from the minion itself, using the salt call commands on the minion and the event module with the fire command. We can pass the data that we want to send inside the dictionary, include a tag to identify the event. So here we're sending a data dictionary with the key data and a single value of message, and our tag is just tag. We can also send events from the minion to the event bus on the master, again using the salt call command on the minion, but this time calling the send function in the event module. We include a tag, in this case, my tag success, and the data we want to send in the dictionary. We can also send an event on the event bus from Python, for example, in a custom execution module. Here we're calling the same event.send function as before, but we're using the dunder salt dictionary to make the call. If we were watching the event bus on the saltmaster using one of the techniques we looked at earlier, once the saltmaster received the event, we should see something like the following. We see the message containing the tag that we've specified, and that data dictionary contains a message item with our message of it works. So seeing all the events show up on the event bus, including our custom events, is great, but we want to actually do something useful with them. Enter the Salt Reactor system. Salt's Reactor system gives Salt the ability to trigger events in response to an event. It is a simple interface to watch Salt's event bus for event tags that match a given pattern and then running one or more commands in response. The system binds Reactor SLS files, similar to Salt state files, to event tags on the master. These Reactor files then define the reactions that should happen when the saltmaster sees an event with a particular tag. We have a couple different reactions that we can set up to trigger based on the events that we are seeing. Local reactions are reactions that run any of the available remote execution functions on a targeted minion or minions. Runner reactions are reactions that execute a runner function directly on the master. Wheel reactions are reactions that execute a wheel function on the master. An example of this type of reaction might be having the minion keys being removed once an AWS instance has been destroyed. Caller functions are reactions that run a remote execution function on a masterless minion. Reactors are set up on a saltmaster in the master configuration file or in a separate file in the etc salt master.d directory. All the events that we want to have reactors set up for are included in a list under the reactor heading. We can include events such as wildcards, such as the two here that watch for salt/minion/**/start and salt/cloud/**/destroyed events. Each event then has a list of all the Reactor SLS files that should be run when the salt master sees an event that matches this criteria. So here we have a very simple Reactor file. The syntax should look similar to that of a state file. Reactor SLS files only have access to minimum Jinja context, grains, and pillar are not available. The salt object is available for calling remote execution or runner functions. In addition to the salt object, the following variables are available in the Jinja context. So tag, the tag from the event that triggered execution of the Reactor SLS file, and data, the data event dictionary. The data dictionary will contain an ID containing the minion ID if an event was fired from a minion, and the data key containing the data passed to the event. So one possible use for these reactors would be to tie them into some sort of monitoring system, such as Nagios, Sensu, Prometheus, or OpenNMS. We can set up a simple reactor that looks for an event with the tag monitor/restart/service. If an event with this tag ends up on our Salt event bus, then it will execute the Reactor SLS file, restart_service, which is found on our Salt master in SRV Salt Reactor. In the event that Apache service running on one of our web servers with the hostname aptly named web server, we can have our monitoring system fire an event onto the Salt event bus by running the following command from that minion or connecting to our Salt master via the Salt API. We're including the appropriate tag, monitor restart service, which tells the Salt master that we want to trigger reactions associated with restarting a service. We're keeping this Reactor SLS file as generic as possible by passing information about the minion, where the problem has happened, and the name of the service that is having the problem as items in our data dictionary. Watching the event bus when this event fires, we'll see an event like this. We see that the event has the correct tag that will trigger the service restarting reactions. We can also see that the items that we've included in the command for the ID of our server and the service that has stopped are now included in the data for this event, but that the ID where the event originated is different and is likely our monitoring server. A restart_SLS file might look something like this. Here we're using some Jinja templating to pull out the service and the ID from the data variable in our event. We're using a local reactor call to the start function in the service module. We're targeting the minion that was included in the data, and we're passing the name of the service that we want to restart. We can expand on a previous example. Here we're again calling a remote reactor, but this time we're calling the apply function in the state module. We're targeting the minion ID that is included from the event data. We're having state.apply call a state file on our Salt master, calling restart_service, and we're passing the name of the server and the service to the state file using pillar values. Inside that state file, we can then use those pillar values. We can pull those pillar values out into local variables using some Jinja. Then calling the running function in the service state module, we can ensure that the service is running. Additionally, we can post a message in Slack letting whoever happens to be on call know that this particular service was restarted. So we can also do some basic monitoring and repair directly within SaltStack. So enter beacons. Beacons let you use the Salt event bus to monitor non-Salt processes. The beacon system allows the minion to hook into a variety of processes and systems, and then periodically monitor these systems and processes for changes. When changes occur in a monitored process or system, an event is sent on the Salt event bus that can be used to trigger a reactor. Salt beacons can currently monitor and send events for many system activities, including file system changes, system load, service status, shell activities such as successful and failed logins, network and disk activity, and beginning in the Neon release, a beacon to monitor expiration dates on SSL certificates. On our Salt minions, we can set up a beacon by adding the configuration to the Salt minion configuration file or to a separate file under etc salt minion.d. All beacons need to be under the beacons header. In this particular case, we're setting up a service beacon to monitor the Apache 2 service. For this beacon, we're including the on-change only and unclean shutdown options. On-change only will ensure that the beacon only fires an event when the service status changes. And the unclean shutdown option tells the beacon to look for a particular file that would have otherwise been cleaned up if the service was restarted cleanly. For example, a PID file that was written out by the service management system. On our beacon, once our beacon has been set up, we might see an event such as this on the event bus if the Apache 2 service was uncleanly stopped on our minion. We have the service name, the minion ID, and the status of the service in question, in this case, Apache 2. Once Apache is running again, because the status changed, we'll receive another event very similar to this, except the status of running will be true. We update our reactor setup to look for the new event that the beacon will be sending. Our reactor file is very similar to the previous example, with one additional pillar value being passed to the state file. We now include the status of the service, and we'll see why once we look at our updated state file. Our state file should look very similar to the previous example. We've included some additional pillar to pull the value of service running from pillar. We're then using that value to determine if we should run the rest of the state file. If the value of service_running is false, then we want to run the service.running function and send a message along to Slack. If the value is true, then the service is already running and we don't need to run the rest of the state file. So the final thing I wanted to talk about today was regarding Salt events and having events on the event bus is engines. So Salt engines are long-running external processes that leverage Salt. They run in a separate process that is monitored by Salt. If a Salt engine stops, it is restarted automatically. And engines can run on either a Salt master or Salt minions. So Salt engines connect to an external system or use an external application to pull information in and place it on the event bus. Some examples of currently available engines that are included with Salt include events to monitor events from Docker, libvirt, or Amazon's SQS service. Additionally, an engine to monitor Slack, acting like a chatbot and feeding commands from Slack into Salt. So on our Salt minions or our Salt master, in order to set up engines, this is done in the Salt minion configuration or a separate master or a separate file under etc salt minion.d or etc salt master.d, depending on where the engine is running. All engines need to be under the engines header. In this case, we're setting up the Docker engine to monitor Docker events on a particular minion. For this engine, we are also filtering the events, so we only receive from Docker. We only want to see events when a container is started, stopped, or when a container dies. Once our engine has been set up, we might see an event such as this on the event bus when a Docker container is started, and a similar one there when the container is stopped. Once these events are available on the event bus, we can use the same type of reactors that we looked at previously with sending events and when using beacons to trigger actions on these new events. So in review, we looked at the various ways, the various built-in event types that Salt uses. We looked at ways to listen for events using the Salt command line tools, the Salt API, or using some Python code. We looked at what a typical Salt event looks like and discussed its various components. We looked at ways we can send events to the local Salt minion event bus, as well as firing an event to the Salt master using both command line tools and using some Python code. We looked at the Salt reactor system and how we can have Salt run execution modules and state modules in reaction to certain events. We also looked at ways we can utilize Salt events and the reactor system with monitoring solutions to restart services. And finally, we looked at how the beacon and engine system can be used to have Salt do some basic monitoring and repair work. And that concludes the talk. If anyone has any questions, I realize this is going to be shown at a virtual conference, so no Q&A during the video. But if you are interested in reaching out to me via Twitter or email, my email is just gareth@saltstack.com, and my Twitter is available on all of the slides. Thank you.